next talk will be given by Professor Ulissi, and he is a professor at Carnegie-Mellon University and one of the co-organizers of this session. And he's going to talk about the limits of scaling relation deviations on intermetallic surfaces. And Zach, I'll ask if there's a way you can put a pointer on your screen. A couple of comments in the chat have indicated, yeah, perfect. That would be super helpful.
Okay, thanks, John, for the introduction. You can hear me?
Yep, sounds great. Go for it.
Perfect. Okay, so Paul already gave a great introduction to some of the problems of scaling relations, so I won't really dive into why we're trying to circumvent these. But I did want to highlight there are a lot of different strategies, and I really like this paper by Javier and Nuria late last year in ACS Catalysis, talking about all the different strategies that we can use to break scaling relations. The things that Paul were just talking about is sort of up in the upper right. So these are dynamic effects, which could either be mechanical or electromagnetic or something else, dynamically controlling the catalyst or altering the properties. There's a lot of ways that you can functionalize materials. And an area that has been talked a lot about is how to make a patchy or heterogeneous or bifunctional surface that has desired properties to get around some of these classical scaling relations. And so I want to talk about a couple of specific examples that aren't necessarily on these five. So one is a class of materials called intermetallics, which are alloys that are strongly ordered. And I'll go into a little more detail why we're interested in these materials. And also p-block doped catalysts, which have been investigated sort of one at a time, but it's been a little bit difficult to get an idea of how their properties behave as a whole across all possible binary or ternary transition metals plus the p-block doping. So intermetallics are quite interesting for a variety of reasons. This is work that we're doing in collaboration with Rob Ryu, Mike Janik, and Zachary Liu at Penn State, funded by the DOE, and also work that we're doing with Shoji and Arena at Hopkins and UC Irvine, respectively, funded by the Sloan Foundation. So a couple of the nice properties are, first of all, these materials are very stable and very diverse. The formation energy can be very negative, which helps to maintain ordering and maintain composition near the surface. There has been a ton of work on the edges of this phase diagram. So at very low compositions of A or B, you get a solid solution alloy, and those have been really, really well investigated in catalysis. But at these intermediate compositions, you can get more interesting surface adsorption sites and more interesting phases than what you would see in a solid solution. The next nice thing is that they're quite synthesizable. There are thermal and wet chemistry approaches for making these. If you go to an experimental collaborator who really likes making intermetallics, you can ask them to make a specific crystal structure and you don't have to worry quite so much about what specific phase you're using. They're verifiable in that because of the long range ordering, it's a little bit easier to check that they are the crystal that you think they are with XRD. And also because they're ordered, sometimes you can get these really nice electromicrograph images that show exactly where the atoms are. And this is a case where there is perfect ordering at the surface for one of these crystals. And the final thing is, in addition to the base crystal structures, they're quite tunable and that you can grow overlayers on top if you want to add some strain, or you can make them hollow with different tricks. And so there's really a wide range of, there's a huge space here that we can investigate if we're trying to get around some of these scaling relations. And these sites look a little bit different than the solid solution ones that we saw previously. Okay, so scaling relation arguments in catalyst design often go something like this. This is sort of a simplified view. We do a lot of really detailed calculations on pure metal surfaces. This is an example from Jens's group, Chuan Shi and PCCP in 2014. This is a scaling relation between hydrogen binding energy and CO binding energy. For the pure metals, this looks really nice and clean. And we do scaling relations both for the thermochemistry and for the kinetics. And then we use that to build up microkinetics across descriptors. So this was follow-up work by Karen, who's going to talk later in Nature Communications for CO2 reduction. This microkinetic model is based on this linear scaling relation. There is a GCO here, and that is changing, but behind the scenes, the hydrogen binding energy is changing based on the scaling relation. And then once we have a plot like this, this tells us that there are maybe some targets that we should be going for. So for example, for CO2 reduction, maybe we want a CO binding energy at around minus 0.4 electron volts delta G. And this also says something about maybe the transition state. If we could tune that independently, we would want it to be about 0.7 electron volts for the transition state energy. Once we have those targets, then we can do a large scale screening via optimization. So we can either do high throughput and just find which materials happen to be in here, or we can do a targeted discovery effort if we can predict properties and then drill down on anything that we predict to be within this region. So in applying these ideas to intermetallics, there are some questions about how exactly do these scaling relations apply and how much can we trust them? Is this loop self-consistent if we have a patchy surface? So people have already thought about how we might want to tune CO and hydrogen binding energies independently. So Jan Rossmeisel had a nice review in 2017 where basically he pointed out that there's a class of materials that are all very strong CO binding and strong hydrogen binding, and they make a lot of hydrogen. You have some materials in the upper right that bind CO very weakly and bind hydrogen weakly, and you make a lot of CO reformate. And then copper in this region sort of has a privileged position, which has an intermediate binding energy. And so when we see a plot like this, and there's basically a hypothesis that we want to move beyond CO, when we're thinking about a new class of materials, really what we're asking is, what space might this class of materials occupy in this graph? And the underlying hypothesis is, if this new class of materials is actually interesting, maybe they would have some properties in this intermediate region we could sort of fill in this area. But exactly how wide this area is and how far we can push this idea is really hard to nail down. And there's always the idea that maybe I should just search more intermetallics or search more alloys or something else. I also like this question that I saw on Twitter by James McCone. He asked in September last year, just posted, I think, for a proposal that he was writing, is there such a thing as a catalyst that selectively absorbs hydrogen from a CO-hydrogen mixture stronger than the CO? And so this question is really rooted in the idea that there is a scaling relation that we saw previously between CO and hydrogen. That's where this idea is coming from. And so on the same plot, what James is actually asking is it possible to find alloys or intermetallics that occupy this region in green, where the CO binding energy is actually weaker than the hydrogen binding energy? And currently, that's really difficult to prove or disprove for a class of materials. Finally, if we take the same microkinetic model that I showed before and we reformulate it in terms of the CO adsorption energy and the hydrogen adsorption energy, then we can see that there is actually an area with really high activity, sort of in this lower right region, and high selectivity. And so we really want to find intermetallics in this region. It seems like microkinetics back up this sort of qualitative argument that Jan was making. So how do we find intermetallics in this? So we've had a system running online for about the past 2 years. This system runs every night. We're trying to find intermetallics with various properties based on descriptor arguments and otherwise. There's an automation component. We run about 200 calculations a day across different intermetallic compositions and surfaces. These are collected in a database. Over the past 2 years, we've done about 100,000 calculations across different compositions and surfaces and different types of sites and adsorbates. We published the CO and hydrogen data already on GitHub, and we're publishing the rest as they come out in papers. If you're interested, shoot me an email. So this runs every night, and we basically target different materials based on likelihood of having interesting descriptors for the chemistry that we're interested in. I'm not going to go into detail about each of these blocks. In order to make these predictions, we need models that can connect atomic structure on the left-hand side with properties like adsorption energy. And so again, without going into details, we can build models that directly do this. So we published this last summer. If you're interested, look in that paper. I'm also going to be talking about cases where we need uncertainty. And so with uncertainty in these same models, we published a paper in MLST in just last month with myself and a collaborator from the machine learning department in order to calibrate uncertainty estimates inside of these special machine learning models. The reason we need the machine learning estimates is because the space is so overwhelming that we can't brute force this problem. And so what I want to point out is when we're trying to figure out what is the adsorption energy on a new surface, a safe situation is one where we have multiple sites on the same surface, and the strongest predicted adsorption energy is one that we've calculated with DFT. And then we have a number of machine learning predictions for all the other ways that we could put an adsorbate on the surface. Maybe there's 3 other different sites here. We also need uncertainty estimates. And if all of those lie above the DFT estimate, then I would say this is a relatively safe prediction on what is the adsorption energy for this intermetallic. If we don't have these machine learning models, we have a problem in that we might have a DFT calculation, but there could be another site that we haven't already considered, like a bridge site, that is actually lower than the DFT one. And so this is a situation where it is actually uncertain what is the adsorption energy, even though we've done 2 calculations on the surface. And so for the rest of this talk, what I'm going to show you is a small subset of the data that we've collected. And it's only the surfaces where we think we're in the safe configuration region, where we have predicted a number of different adsorption sites. And the lowest one among all of the predictions and all the DFT calculations is a DFT calculation, so that we can actually point to it and say this actually came from a specific functional, and we trust this number, and everything else we think is a higher energy. Okay, so moving into the data that we've collected, this is currently unpublished. We've done a lot of calculations on oxygen and OH for oxygen reduction. This is one of the simplest examples. It's a situation where we expect relatively strong scaling. So oxygen sitting on a surface binds to a central oxygen. OH sitting on a surface also binds to an oxygen. And so a very simple physical model says that probably if you strengthen the binding energy of this one on the left, you'll strengthen the one on the right as well. And so now this is a set of calculations. Every point is a prediction for a different intermetallic surface where the strongest adsorption site was DFT calculated. There's about 500 or 1,000 points here out of about 500,000 different surfaces that we can consider across the entire intermetallic composition space. So these orange points are metals. Unsurprisingly, the metal one-on-ones obey a really strong scaling relation. Among all the intermetallics, there's quite a bit more spread than the pure metals. And so the pure metals have a spread of about 0.3 EV. Among the intermetallics, that's a little bit larger. So we can shift this by about 0.5 EV up or down. The other interesting thing is that for this chemistry, oxygen reduction, the target, if we could break all the scaling relations, is at about 1.23 EV delta E and about 2.4 for the oxygen adsorption energy. And so what this tells us is that it is not a big ask to find a material that has these optimal properties. We are on the edge of this overall distribution, but that is a very reasonable thing for us to search for. If I was a betting man, I would say that I can probably find materials in this region because we already have a few points close by. If we work really hard, we could probably find more points. Let's go to a slightly more interesting case. So this is another situation where we expect strong scaling. OH and OOH both bind to essential oxygen. And so we would expect there to also be a strong scaling relation, and this is the basis of a lot of oxygen reduction materials discovery efforts. In this case, it looks pretty much the same, but there are these outliers down in the bottom left that basically say it is possible to break the scaling relations as long as you have a material that binds oxygen so strongly that it goes into a bidentate configuration. And that's a situation that would have been difficult to find by hand, but sort of occurs naturally. If we're interested in that, we can fill it in. Unfortunately, this is still far from the peak in terms of OOH and OH. Let's go back to that CO and hydrogen scaling that was so perfect for the pure metals. So on these pure metals, we have a really nice linear relationship, but across all the intermetallics where you have different sites, there's actually a huge amount of spread between the CO binding energy on the x-axis and the hydrogen binding energy on the y-axis. We can deviate off of the scaling relation by about 0.15 or 0.2 EV, and more in some cases for some of these intermetallics. So this plot for intermetallics looks nothing like this really perfect linear scaling relation. And so that means that we probably have to go back and revisit some of the microkinetics if we're going to go to a bimetallic surface. James was asking, is there a catalyst that binds hydrogen more strongly than CO? And I've outlined this red region. That is basically the question that he was asking. And so after an analysis like this, based on the calculations we've done without targeting this area, I can say with some certainty, yes, probably you can find materials that are like this if you have a certain class of properties. all of these things we can also automate and put online. Let me just bring up really quick. So this is all sitting on Plotly. I'm happy to share the plot afterwards, but we can go back and interrogate all of these things and look at where things were sitting, the formula, the coordination, what Miller index, where it was coming from, what the composition was. This makes it really easy to go back and play around for different chemistries. Okay. So like I said, we can also do the same thing for other materials that are not intermetallics. We haven't been focusing on these other ones, these p-block dope elements, but carbides, hydrides, sulfides, silicides, nitrides, we have a lot of data as well. Our preliminary data says that you can get quite a bit more deviation from scaling relation in these materials in the intermetallics. And this is unpublished data that we're currently working on. If you're interested in these sort of p-block dope elements, feel free to shoot me an email. Okay, so a quick summary. We're working to try and get property bounds for systems with diverse sites. And these intermetallics seem like they have a lot of possibilities for breaking the scaling relations, at least compared to the pure metals, as long as you have different anchorings. The pure metal scaling relations are not a great assumption for these intermetallics, so there's sort of an open area of literature here that we need to fill in. Carbides, hydrides, nitrides, sulfides can deviate a little bit more, but this is unpublished data we're still trying to verify and collect more calculations on. And if you're interested, feel free to shoot me an email. I'm happy to share the data, the analysis. We sort of have more than we know what to do with. And the next steps, I think, are really coming up with ways of defining rigorously what are the confidence windows on class of materials. So can we guarantee or can we prove that we have found maximal properties for something like intermetallics? And basically, when do we know when to just move on and target another material if they aren't going to satisfy the properties we want? And the other thing is active learning to specifically target materials that break scaling relations is an open area of research. So with that, I'll just thank all the students and especially Kevin Tran and Perry, who did most of the calculations and did most of the data analysis that went into this talk, and various funding agencies that have funded this work. Thanks.
All right, thanks, Zach. We have one question right now, and that is, can you elaborate on the binding energy plots with respect to the work function of the metal? And they're particularly interested in how the binding energy for CO versus the intermetallic work function compares to any correlation of hydrogen binding energy versus work function.
Yeah, that's a great question. We haven't been calculating, or we haven't been collecting the work functions from these, but that's something that we could go back and do quite easily. I think if you can come up with a local descriptor, you can probably make these arguments. But really what we're looking at is a surface where some elements like CO more strongly than the hydrogen. And so if you just look at work function of the entire material, you're probably going to get similar spreads, right? If you assume that there is one hidden variable behind this, you're not going to be able to explain all of the variation inside of the data set. But if you can come up with something more local, you can probably get at these arguments. That's basically what these graph convolution models are doing.
Okay. Speaking of graph convolution models, the next question is, does the graph model work for any chemistry, or do you make a separate model for each chemistry? I'm assuming what this means is that the question is there one model for all the intermetallics or a separate model for each intermetallic?
Yeah, that's a great question. There is one model for all the intermetallics. So in terms of the materials chemistry, there is a single model across compositions. That's the reason we're using these methods. That's a very nice property. However, we're currently building different models for each adsorbate. And so the CO model is separate from the hydrogen. We can use one model to train on both CO and hydrogen at the same time, but we currently don't have any data to suggest that it's doing any better than seeing the CO and hydrogen separately. And so coming up with improvements on this model structure so that you can either capture the prior that we know that there probably is some scaling relation between these adsorbates, or coming up with a system that learns from multiple adsorbates at the same time is something that we're really interested in and trying to work on now.
All right, I think the next question is, do you have any thoughts on why there's so much scatter in the scaling relations of the intermetallics? For example, is there a chemistry point of view or some variant that you're not accounting for? And if so, what would that be?
Yeah, It really gets at the fact that you have an ordered surface where you're exposing two different elements. And so unlike a solid solution where you tend to have clustering or it tends to be more of an ensemble effect, you can get really interesting behaviors. So here, for example, you have an edge site that is specifically just one yellow atom, so I guess nitrogen in this case. In a solid solution, you might not have only singlets or only nuclearity 1 sites. You might have a wider distribution that sort of averages out different effects. It's due to this really strong ordering at the surface and the fact that you have two different elements with unique properties that leads to this deviation. If you have a solid solution, that's much more well modeled with sort of a scaling relation argument.
All right, I think we'll do one more question, and then we'll break for lunch. There was a question about what parameters are you able to vary when you automate the generation of the different structures? How do you automate the different surface positions and terminations?
Sure. So we published an overview of the workflow that we have in JCIM in 2018. So I would refer to that. We also have all of the information on the automation up on GitHub. If you just search for Ulissi Group GitHub, the package is called Gatsby. It's all open source, running on open frameworks like Fireworks and other things. But I'm happy to go into more details. Just shoot me an email if you have follow-up questions.
All right, there's a few more questions in here, but I think we'll break for lunch or coffee or whatever your time zone finds appropriate. I will copy all of the questions into a Google Doc, and Zach, you can put some written responses there later. I think now we are on schedule for a break. So Omar, if you want to put the break slide up with the schedule, we will resume at 12:30. And at 12:30, Omar will be giving us the